Good day, students. Today we shall look into another property of light, diffraction. And in particular, we will study single slit Fraunhofer diffraction. Now this is the image of a blade, a razor blade, seen through laser light. If you look closely, you will be able to see diffraction patterns on the outer edges of the razor blade and also on the inner sides of the razor blades. Now let us look into what is diffraction. It is the bending of light around small opaque objects and their encroachment into the geometrical shadow. So if you have an opaque object and it is very small, when light happens to fall upon it, naturally we assume that in the shadow region there will be no illumination. But the light can bend around that opaque object and it can encroach into the geometrical shadow and produce a small amount of light in the shadow. That is why our shadows are not completely black. Now this was first observed as a physical phenomenon by Grimaldi and later on explained by Augustin Jean Fresnel. He explained that it is the mutual interference of the secondary wavelets originating from various points of the wavefront which are not blocked off by an obstacle or allowed to pass through the slit. Okay. So if we have a source of light S and it emits rays and we see the wavefronts from it, on the wavefront, each point of the wavefront acts as a secondary source for secondary wavelets. Okay. Now if this is your source S, we have wavefronts emitting from it, and each point on the wavefront will act as a source of secondary wavelets. This will act as a source of secondary wavelets. This will act as a source of secondary wavelets. This will act as a source of secondary wavelets. This will act as a source of secondary wavelets. Okay. And all these secondary wavelets can mutually interfere among themselves to produce the diffraction pattern. Okay. Now this bending of light or deviation of light becomes noticeable when the dimensions of the obstacle or opening are comparable to the wavelength of light used. Okay. Now here in this figure we have light falling on a slit. Okay. So in between these black lines we have the slit, and light is passing through the slit and all other regions are blocked. Now if the slit is large enough such that the wavelength of light cannot be compared to the slit. Okay, so the slit size is very much larger than the wavelength. On the screen here we will be able to see only the shape of the slit. Okay, so in this graph that you see here, you will be able to see the intensity profile. That is, it will be in the shape of the slit. Okay. But if the slit size is reduced, okay, now if the slit size is reduced, here we can see that when light passes through the slit, here again the slit acts as a source of secondary wavelets, okay, and produces the spherical wavefronts. And these spherical wavefronts, each of the wavefront will produce secondary wavelets, and these secondary wavelets will again mutually interfere with each other. And this interference between these secondary wavelets will finally produce the diffraction pattern. And the intensity profile of the diffraction pattern is given here. Now there are actually two classes of diffraction, Fraunhofer diffraction and Fresnel diffraction. Let us distinguish between them. In Fraunhofer diffraction, the source light and screen is at an infinite distance from the diffracting element. Okay, so here in the previous example, the slit was a diffracting element. Okay, light was diffracting through it, was bending through it. So here in Fraunhofer diffraction, the source light should be from infinite position and the screen should be at an infinite position. That means the wavefronts coming towards the slit and emerging from the slit should be planar. Okay. Whereas in Fresnel diffraction, the source light and screen is at a finite distance from the diffracting element. That is, it should be nearer to the diffracting element. In that case, the slit will see either spherical or cylindrical wavefronts coming towards it and going away from it. Here, the incident wavefront and diffracted wavefront are plane. Okay, for Fraunhofer diffraction. Here, whereas for Fresnel diffraction, here the incident wavefront and diffracted wavefront are spherical or cylindrical. Now, Fraunhofer diffraction is easier to view in a spectrometer, whereas Fresnel diffraction is not easy to view using a spectrometer. Now let us look into the setup for Fraunhofer and Fresnel diffraction. In Fraunhofer diffraction, we said that the slit needs to see light coming from infinity. That is, the source light should be at infinity, and the light emitting from the slit should go to infinity. Now, to create such a condition here, what we do in the lab is that we place a source light here, and in front of the source light we place a converging lens, a convex lens. Okay. Now, if the lens is placed at focal length distance in front of the source, okay, f distance in front of the source light, the emerging rays from the source will be made into parallel rays by the lens. That is the property of the convex lens. Okay, so the slit now sees parallel rays, and in effect it feels that the source is at infinity. Again, the rays emerging from the slit will be almost parallel, and in order to view these parallel rays on a screen, we need to focus it, and hence another convex lens is placed, and that focuses the light onto a screen. Now, in the setup for a Fresnel diffraction, we will not be using these convex lenses. Okay, so the source light is placed in front of the slit, and the spherical waves or cylindrical waves from the source fall on the slit, and again it undergoes diffraction, and the waves emerging from the slit will be again spherical or cylindrical depending upon the nature of the slit, and these wavefronts are viewed on the screen. Now let us look into single slit Fraunhofer diffraction. Now in this setup, the source light is placed at a particular position, and in front of it we place a convex lens. The convex lens is placed so that the emerging beam from the source is made into parallel rays, and parallel rays happen to fall upon this slit. So the slit sees parallel rays coming towards it, and hence it feels that the source light is at infinity. Let the dimension of the slit be small a, and monochromatic light lambda fall upon it. Hence, rectangular slit of width a is illuminated by monochromatic light of wavelength lambda, and here the source is at infinity. When light passes through the slit, it undergoes diffraction. After diffraction, light is focused on the screen by means of another convex lens. On the screen, a diffraction pattern is observed. Here, this is the diffraction pattern that you can observe, and on the central region at point O, the central maxima is obtained. It is flanked on either side by a number of dark and bright fringes called secondary minima, secondary maxima, secondary minima, secondary maxima. On either sides there are a number of secondary minimas and maximas. Now, when light falls on the slit becomes a source of secondary wavelengths that spread out in all directions. Okay. And at the central point O, all the secondary wavelets from the slit will emerge towards that point, and they will have the same phase and hence superpose to produce maximum intensity. All the light rays coming towards O will have the same phase and they will superpose to produce maximum intensity. Whereas at any other point on the screen, let us assume a point P. Okay. So at this point P, these diffracted rays are making an angle theta with respect to this optic axis, and they will not have the same phase. All these rays will not have the same phase, okay, and they will cover unequal distances to reach P. Now at this point, this ray will travel shorter distance to reach P, whereas the ray coming from this point will have to travel a longer distance to reach P, right? So let us calculate the path difference between the rays at these two extremes. Now to calculate the path difference, we draw a normal from one of the ray to the other. Okay, so this becomes the additional path traveled by the ray. The path difference between these two rays is this region. Now in order to calculate that, what do? We take sine theta at this position. So by geometry we know that if this angle is theta, this angle will also be theta. Okay, and hence sine theta will be path difference divided by dimension of slit small a. In another terms, we can write path difference is equal to a sine theta. Okay. Now let the point P be a region of minimum intensity. Okay. So at P, we are assuming that the path difference to be lambda. Now let this slit be divided into two. The first set of rays, let them have a path difference of lambda by 2 among themselves. Okay. And the second set of rays passing through the slit, let they have a path difference of lambda by 2 among themselves. Okay. Now when these set of rays travel through this medium and reach the point P, the total path difference between all these rays will be lambda by 2 plus lambda by 2, that is lambda. That is, first set of rays will cancel out the second set of rays, and hence P becomes a point of minimum intensity. Hence the condition for minimum intensity becomes path difference is equal to integral multiple of lambda, where n can have values 1, 2, 3, etc. Path difference was obtained as a sine theta n, it is equal to n lambda, hence sine theta n is equal to n lambda by a. Since the diffracting angle theta n is very small usually, sine theta n can be approximated to theta n. Thus, theta n is equal to n lambda by a, where n is equal to 1, 2, 3, etc. Here theta n is the angular width of the nth order secondary minimum. When n is equal to 1, we get the angular width of the first order secondary minimum. That is, we get the angular width of this secondary minimum. Okay. Now if n is equal to 2, we get the angular width of the second secondary minimum, that is this. Likewise on either side. This is the first order secondary minima and this is the second order secondary minima. Okay. This is the equation of importance. Now, at P, if the path difference between these emerging rays is lambda by 2, it is a point of maximum intensity. Here, if the path difference is lambda by 2, we have to take into consideration that the slit is divided into 3 regions. Now, if the path difference between these 3 sets of rays is lambda by 2, that is, the path difference between the first set of rays is lambda by 2, second set of rays is lambda by 2, and again third set of rays is lambda by 2. Okay, the first 2 sets will cancel out among each other, whereas the third set is remaining. Okay, hence when all these rays superimpose at a point P, they will produce a region of maximum intensity. Okay, so the condition for maximum intensity is that the path difference should be an odd integral multiple of half wavelength. Okay, that is 2n plus 1 into lambda by 2. Path difference is a sine theta prime n is equal to 2n plus 1 lambda by 2. Here the angle is denoted as theta prime because this shows the region of maximum intensity. Sine theta prime n is equal to 2n plus 1 lambda by 2a. Since the diffracting angle is small, it can be approximated to theta prime n. Thus, theta prime n is equal to odd integral multiple of lambda by 2a. And n can have values 1, 2, 3, etc. Theta prime n is the angular width of the nth order secondary maximum. That is, if n is equal to 1, we have the first order secondary maxima at this position and theta prime n will give the value for that. Likewise on this side. And if n is equal to 2, we get the second order secondary maxima. That is this region and this region. Okay. This is the equation of importance showing the condition for maximum intensity. Now, at the first secondary minimum, we have these two conditions, that is, theta is equal to y by d and theta is equal to lambda by a. Now, the first equation, theta is equal to y by d, that is obtained from, let the central position be at point O here, okay, and the distance from O to P is y, okay. If the angle between the diffracting ray and the optic axis is theta and the distance from the slit to the screen is capital D, we have the expression that angle theta is equal to arc by radius. So from that we get angle theta is equal to y by d. Okay. And in the condition from minima, we get the first secondary minima theta at n lambda by a, where n is equal to 1, that is theta is equal to lambda by a. Okay, so using these two conditions we can write y is equal to lambda d by a. Now the width of the central maxima is actually 2y, right? So if we have a region of first secondary minima here, we have a similar first secondary minimum here too. Okay, and the distance again from the center to this secondary minima will be y. Thus the width of the central maxima will be 2y. Thus 2y is equal to 2 lambda d by a. The width of the central maxima can be obtained as 2 lambda d divided by small a. The width of the central maxima is large for longer wavelength and narrow slit. That comes from this expression. Lambda is in the numerator and small a is in the denominator. Hence, the width of the central maxima is directly proportional to wavelength and inversely proportional to the slit width. Hence, we can say the width of the central maxima is large for longer wavelength and smaller slits or narrow slits. Likewise, the width of the central maxima is small if the wavelength of light used is shorter and the slit size is larger. Now this is the pattern we get from a single slit Fraunhofer diffraction. Now the difference is that in the wavelength of light used. The image shown above uses monochromatic red light, whereas the image shown down uses white light. When monochromatic light is used, the diffraction pattern consists of alternate dark and bright bands, whereas when white light is used, the central maxima is white and the rest of the diffraction bands are colored on either side. That's all for today's session. Thank you.